Yay. Okay, are you ready? Today we get to do power series because we're powerful. Okay, that was my attempt at we are Hans, we are France. Pump you up. Okay, power series. So what's power series? Basically, we're gonna have those infinite series that are involving x's and n's, both. And they're gonna turn into Taylor polynomials. Okay, not too bad, but they make us feel powerful. So power series just means you have x's and n's. We've got two variables, so it's gonna be a good day. Here we go. So here are your essential questions. Hopefully you can get those answered by the end of this lesson. If not, we'll talk about them in class together. Okay. And here's the objective from AP Calculus. So let's get started. So this power series, what is it? It's basically just mixing the x's and n's. It's taking that infinite series that we had learned back in part one and also doing some x stuff with it. And the x stuff could be centered at 0, it could have a different center, all kinds of fun things. So we're going to see how this power, I know you guys are like, stop it, how this power series can match, again, the crazy function that we're trying to match, like sines and cosines and all kinds of crazy stuff. So here we can see this power series. It's centered at 0 because I don't see any x minus in here. So this part right here would be the a sub n part, and here is what makes it now a power series. So this is what makes it the power series, centered at -1, because remember it's opposite of inside. And there's that a sub n part, which is actually just making it alternate. Here's the power series. There's what makes it the power, centered at 1. And there's my a sub n part, which was that harmonic series that we knew from before. Okay. So we are going to have 3 different options for what can happen with the convergence. So just like in a tangent line, we can have whatever we're finding only converge at where we are centered. So it still only converges at one point, even if I have this wonderful polynomial, okay, but it still could be just like the tangent line and only converge at where you're centered. It could converge maybe for part of the series and then it goes away. So it can converge just on some, like here I'm centered, just some radius around where you are centered. So just on an interval, everything matches and then the rest doesn't match. Or what we love the most is when it converges everywhere. So the graph matches the polynomial everywhere. So your radius of convergence here, like as you go out from your center, would be infinity because it's going forever and ever to match. And so those are going to be the 3 things that we are looking at here. Okay. And the ratio test is going to be our BFF as we do these and find out how they are matching. So let's just review the ratio test really quick. As I go to infinity, I do the a sub n plus 1 over a sub n, and I can have 3 different options. Less than 1, greater than 1, equal to 1. Less than 1 is when we are converging, and that's what we're going to kind of really be looking at. So this right here is what we really are going to try to see, okay? If we are greater than 1, then we're going to diverge except for at the 1 point. And then when we're equal to 1, that's that IDK, don't know, try something else. Okay, but this is what we're really going to focus on, is we're going to try to find the limit and then say, where is that limit value less than 1? Paper. So let's look at the first one. It says find the radius of convergence. So I know that this is almost always telling me to use, and we're going to see when it's not, but it's almost always telling me to use that ratio test. Okay, so I'm going to take the limit as n goes to infinity of the absolute value of that guy to the n plus 1 divided by the original. Reduce. And I'm just left with 2x. Sorry, that's an n. That's an n. And here, now I have this, there are no more n's to put in, because it's like 2x to the first, right? Those n's. Okay, so there are no more n's to put in. This is like saying, what's the limit as x goes to infinity of like 5? Well, there's nothing to plug in there, so we would have said 5, right? This is very much the same thing. There are no n's to plug in, so I just have the absolute value of 2x. Okay, so that's kind of my first step, is to use the ratio test. Then we said, or the limit part of the ratio. Then we said in the ratio test, so we're going to continue with that. This right here, this output, has to be less than 1 to converge. Agreed? Kind of think about that. So we were using the ratio test, and we had the 3 options, and we said it only converges when we get less than 1. So that's what we want in order to find the radius of convergence. So then I'm going to try to get it here into the whole goal is to find the x minus where you're centered is less than this radius of convergence. So I'm going to go ahead. Sorry, I don't know why I just did that. Got ahead of myself, guys, sorry. So I'm going to go ahead and pull the 2 out from here, because that's fine. And then I can see that this is x minus 0. X is just x minus 0 is less than 1/2. This is my radius of convergence. Okay, so you're like, what does that mean? So for this Taylor polynomial here, when I am centered at 0, I go out 1/2 away from 0, and for all of that interval, the function will match the Taylor polynomial. So what does it do out here? It diverges. And this is the tricky part. What would have happened at 1/2? What if I plugged 1/2 into here? What would I have gotten? 2 times 1/2? 1. Absolute value, 1. What do we know about the ratio test when I am 1? We don't know anything. So at these endpoints, though, we don't know yet what's happening, and we'll have to go do more work. Because even at, like, look at negative 1/2. What's 2 times negative 1/2? Negative 1. Absolute value, 1. So we don't know what's going on. We have to do more work, okay? But my radius of convergence is 1/2. So everywhere from the Taylor polynomial to the function that we're talking about, we are matching. It is altogether matching between negative 1/2 and 1/2. And then it starts to diverge off. But I've got it matching for a while, which is really cool. How can we get it to match longer, right? That's always our question. But okay, so let's look at this one. Find the radius of convergence. What's the first step? Well, we're going to set up for the ratio test. So we take the limit as I go to infinity of the absolute value, and we plug in n plus 1. So I'm going to go ahead and distribute in my head n plus 1 divided by, so since I've already got the fraction, I'm going to flip and multiply by the reciprocal. Okay. So let's simplify that a little bit on the inside before I take the limit. And I have, again, no ends left. So this is just, if I have no ends to plug in, it's kind of like saying the constant when I went to infinity. So I am left with this right here. So that's the first part of the ratio test. The second part is saying, well, where does that converge? So we are looking for where this limit that we just got is less than 1, because any x values where that happens tells me I'm going to converge by the ratio test. So I'm going to multiply the 3. I'm going to use what we talked about in that pre-series by taking the square root out. Sorry. So I'm going to go ahead and square root the square out so I can square root. And now we're in the form that x minus c, because we were centered at 4, is less than my radius. You agree we were centered here at 4. So that's where we want to stop for the radius of convergence. So there is my radius of convergence. So when I am centered at 4, I'm going to go out 4 plus the radical 3 and 4 minus the radical 3. And I know that everywhere I will match on that interval. So all of these values that I plug in for x are going to converge. All of these out here will diverge, and the endpoints are to be determined. So what's the next step? What do you think the next step is? Find out what the endpoints do. Okay. So what happens at the endpoints? So we've kind of talked about when I have the endpoints, that's where the limit as I go to infinity of that a sub n plus 1 over a sub n equals 1. So that's where they are inconclusive. So, or our IDK, as we like to say. So we have to go figure out what the endpoints will do by plugging them in separately and using one of the tests we learned back in part 1. So see, it just keeps continuing. Unless we have a geometric series test. If our series was a geometric series, the endpoints will always diverge. Why? So when I have this a times r to the n, remember diverging is when the absolute value of r is greater than or equal to 1. So I know what happens at that equal to part in this case. In the ratio test, the equal to 1 was IDK. But in the geometric series test, when they're equal to 1, I already know that diverges. So if it's geometric, we don't have to check endpoints. And you guys will be like, I love you, geometric. Thank you. I don't want to go check all those endpoints and use all those tests over and over. Thank you. Okay, but so you don't have to check endpoints because we know that they diverge. If we have used the ratio test, and we're not doing the root test this year, but if we had used the ratio test, you must check endpoints. And FYI, this is a lot of work. Work. Okay. So let's look at this one and let's get just kind of more conceptually down again what we're looking at. And then we'll go do some more of the harder problems. Okay, so here is the power series. There's my series part. That's what makes it a power. Where are we centered? Hopefully you guys are all like, we're centered at 1. So I'm going to kind of look and say at 1, that is my center. Then it says that this endpoint over here at 5, or it doesn't tell me it's an endpoint, it just says at 5, we conditionally converge. And then, so I'm going to kind of see what happens. I went out 4 here. I'm going to go out 4 that way to see where I would be. And that would put me over here at -3. Now, let's kind of go back up to this really quick on the ratio test. So when I get less than 1, this is a convergent. And not only was it a convergent, but since we did the absolute value, do you remember on the ratio test, it is absolutely convergent. Actually, I should have probably wrote that to begin with. But not only do I know that's where we converge, but I know that we are absolutely convergent there. We learned that back in part 1. So the only place that we could be absolutely or conditionally convergent or divergent even, is the endpoint. The endpoint is the only one that has the option to do anything, okay? So within the interval, absolutely convergent. Outside the interval, divergent. Endpoints, those are the wild cards. They can do anything. So in this problem, it said that 5 was conditionally convergent. So that's why I almost slipped when I was saying it. 5 has to be an endpoint because endpoints are the only thing that can be conditionally convergent. So if I know that that's an endpoint, everything in here has to be absolutely convergent. Everything on the outside is divergent. And then I have no idea still from the information they have given me what happens at the other endpoint. That other endpoint can do anything. So now let's go see what they give me as options and which one is true. Okay, so then they said converges at -4. -4 is out here, and that is not in converging land, that's diverging. Conditionally, again, -4 doesn't converge at all. It's in divergent land, not absolutely, not conditionally. Conditionally, it's done. But I do know it has to diverge at 4. It is in the divergent land. So we do have enough information to know that -4 diverges. Take a second, write down your thoughts on that, like pause it, make sure you really kind of get if you had any little aha moments, and get those down. Okay. Okay, so we are going to do biggie all together for this one. So here's my first biggie problem. This is my a sub n. This is what makes it the power. Okay. Where are we centered at? Okay, so we know that part. So let's go ahead. If I'm looking for the interval of convergence, I need to start either with a ratio or a geometric. This is not geometric. I don't see my a times r to the n. Okay, this is not a geometric. So I'm going to start with my ratio test with the limits. I'm taking an absolute value. So when I take an absolute value, anything that's alternating, I don't need to worry about. It's gone. So I just need to worry about the stuff that's not the alternating. So my a sub n plus 1 over my a sub n, basically. Okay. So as I see this, I'm going to rewrite it. And I'm going to rewrite this one more time so you really understand like what it is that you're seeing. We're taking n to infinity. So this is kind of like x n plus 2x over n plus 1. And when we're taking the n to infinity, we really only want to see is n bigger on top, bigger on bottom, or the same. Well, n in this case is the same, so I know I am getting out my coefficient of x over 1. So we know that we want to know that we're looking for where it converges, so we're looking for this. We are centered at 0, so I know that this guy is my radius of convergence. So I'm centered at 0, and I go out to 1, and I go back 1 to -1, and everything in here is absolutely convergent. Everything out here is divergent, and then we do not know what happens at the -1 or the 1. So we need to go plug in -1 and 1 into the original series and see what happens. So I'm going to go back to the original series, and I'm going to do, let's go ahead and do 1 first. So this would be 1 to the n. So we're plugging those values in, so the endpoints of 1 and -1 back into the original series so that we can see what this series does. Okay, so let's simplify this. Well, 1 to the n, do I even need it? Nope, because that's always 1. So this series is actually this. So what test do you want to use for this? I would look for the alternating series test. So the first thing I'm going to do is take the limit as I go to infinity of the non-alternating part. And I see that that goes to infinity, which boom, we don't even have to go any further with the alternating series test because this is not 0, so it diverges by the nth term test. Oops, t. So up here, I know that this endpoint diverged. And the endpoints, I mean, like I said, they have a mind of their own. They don't have to do the same thing. They get to do whatever, okay? So you really have to go, unless it's geometric, you really have to go see what happens. Okay, so let's plug in -1 and see what happens. So I'm plugging in the -1 to the n. So now when I reduce it, I need to put those two together. So power, in the power, I add those two, so that would be 2n plus 1. And hopefully you guys are all like, we've practiced this, and you can see that this is just -1 to the first. So when I go to simplify that, and if that's still confusing, ask me in class. We will definitely work it out together. But this is just -1 times n plus 1. And when I'm doing series, sometimes it's easier to just put a denominator. So this is one where I'm like, bigger on top, bigger on bottom are the same. Bigger on top, so boom, this guy diverges by the nth term test. Because it is definitely bigger on top. So I know now that this other endpoint also diverges. So when I am looking at that x, I know that the endpoints are not included because they both diverge. So if they were included, I would have had the bars here, but they are not included, so I'm taking away, like, yeah. So I do not want the bars. And that is my interval of convergence. Or you could write it like this. So if they were included there, it would have been brackets. Brackets include things. Okay. Let's do a couple more. This one says, find the interval of convergence. This is not a geometric series test. I see this hodgepodge with factorials, so I'm going straight into my ratio. I'm going to go ahead and distribute when I plug in my n plus 1. Same thing down here. And let's rewrite that. Okay, 3n plus 3, 3n plus 2, 3n plus 1, and then I finally get to that 3n where they would cancel with the factorials. Okay, so now I'm looking at the limit just on the n's. The n's are only on bottom. There are no n's on top, so this is definitely bigger on bottom as I go to infinity, which would give me 0. We love, love, love limits that give me 0, because this is always, always, always less than 1. So guess what? This converges everywhere. It matches from negative infinity to infinity. This power series matched whatever function it was trying to match forever. Okay, so this is going, if I'm looking, my radius is infinity. I mean, it matches everywhere. So I would go from negative infinity to infinity. So cool. Okay. Let's do another one together. So here, this is now a geometric series. I can see that I have 1, and now this r, there's no n's in here. So there's no n's. X's are okay. Okay. To be inside is now my r to the n. So when I have that with geometric, if you remember, I want to look for where this guy is less than 1. And we know that geometric series, the endpoints always diverge. Bless, 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 bless. We don't have to go check endpoints. So let's go back up to this one right here. So I'm looking where this 2 over x squared plus 1 is less than 1. So I'm going to go ahead and multiply over this x squared plus 1. And it is positive because it's an absolute value, so I don't change my signs. So this is what I'm really kind of looking for. So if I think about my x squared plus 1 graph, this one's really hard to do algebraically. So here's this x squared plus 1, and I want to know where it is greater than the 2. So I'm looking here where we are greater. So this one's a little bit trickier, but hopefully like you can see that when I plug in a 1, I get 1 squared plus 1, which is 2, and negative 1, same thing, okay? So I am greater when I am less than negative 1, but greater than 1, and I do not include, so there should not be any underneath parts or equal to because this is geometric. So this answer is D. I know it like looks smaller and simpler, but this one's tough. So like if look at it again, kind of pause and let it sink in or ask me some questions when I see you. Okay. Go to the next one. Here's the a sub n part. Okay, well that's nice that they told us. There's the a sub n and there's the power series part. I can see that I am centered at 2, and it wants me to find the interval of convergence. So this is not a ratio test or not a geometric series test. I do not have an a times r to the n going on here. I've got n's and ln's of n's. So the only two things here when we're looking for the interval of convergence are ratio or geometric. So this one, we're going to go to ratio. See if you can get this set up. Try to pause me and see if you get this without me. Okay. This one. See if you can simplify it without me as well. And then see if you can take the limit without me. Bigger on top, bigger on bottom are the same. The same. And look, this limit's already set up in my x minus c. So that's awesome. And we are looking for where that is less than 1. So we've already said that this is not geometric. So if I'm centered here at 2, I'm going to go out 1 from here in both directions. So I do not know what is happening here or here yet. So I have to go check those endpoints. So let's go check when x is 1 first. We're going to plug it into the very original. See if you can do that without me. Try to go plug in your 1 and simplify anything. Okay, so I got this one. I can see that this is a geometric series. Why'd I just say that? Alternating series. This is an alternating series test. And I can see the terms are decreasing in absolute value to 0. So as I go to infinity of this, non-alternating, I get 0. And here I can see that my terms are decreasing. I'd get bigger on bottom each time. So I know that the terms are decreasing in absolute value to 0. So this guy converges by the alternating series test. Okay, so we know that 1 is included. Let's go see what happens at 3. Okay, so on this one, I got 1 to the n, it's just 1. So there's no alternating part left. So you can pick a series now that you think would work for this one. I actually see the integral test pretty quickly, but I know we don't like that as much. But this one, when I see a u sub with it. So u is the ln of n, and then the derivative of that is 1 over n. So this one to me, I would have just went to the integral. I can see that this right here is positive, continuous, and decreasing for n greater than or equal to 3. So it's met my conditions. So when I look at this integral, then I can see a u sub again, like I said. This would be the ln of 3. The ln of infinity is still infinity. So this is kind of like going to infinity here. Okay. So I should have wrote it how we learned it. I won't do it. Call that B. Now we want the limit. So this would be the limit as b goes to infinity. The ln of the absolute value of b minus the ln of the ln of 3. That goes to infinity minus something small is still infinity. So this diverges. So I know that 1 converges and 3 diverges. Or you could have wrote it like this. Okay. Okay. On this next one, the first thing I'd kind of do is see they've given me the nth term. And what's nice is that nth term is pretty much just the series that I want in here. It's that power series. And I just need to see where I'm starting here. And so, excuse me, usually want to check either at 0 or at 1. So if I plug in a 0, that's the only thing that's going to give me the 1 here. So I know I'm starting at 0 and we can check everything else and it works. Oh, sorry. So this is the power series that this would be equivalent to. So use that nth term to help write your power series. And it's looking where we converge. Hodgepodge, definitely not a geometric, so we're going to have to do the ratio. Hopefully you guys can see if you can do this without me. And then just kind of check as you go with what I'm doing, or just pause me and then see if you get the same thing. So I got the limit to be 0, which we love, because that means that whatever this f of x was, this power series matched it for f. So super cool. Okay, so we're going to pause there on this day 2. We call this part 1. Give you a little break, and then when you're ready, come back for more.